Hello everyone, welcome back to PMAC1140. In this video, I want to start the last chapter of the course, chapter 12, and we'll be talking about two important concepts in pre-calculus. It is series and sequence. Okay, so that is in the first section of chapter 12, is section 12.1. So let's get started. Section 12.1 sequence and series. Okay, so first of all, I'm going to talk about sequence first. So I'm going to try to split up into two videos. Hopefully I have enough time that I can combine all sequence and series concept in one video. Okay, if you guys remember the first time, the first chapter of college algebra, we talk about set, right? A sequence and series over here is kind of related to the set concept we learned in college algebra. Okay, and you guys already know set is a collection of element, right? Member, right? Or it could be a collection of number. Okay, so on the first part of this video, I will be talking about sequence, and we'll be discussing how sequence relating to the set concept. Okay, alright. As I say, set is a collection of number. A sequence is also a collection of number. Then what is the difference between sequence and sets? For sequence, the list of the number must follow a certain rule. Okay, it must be in a very specific order. In set, it's no order. For example, I just have a set of all the even number, okay, from 1 to 10. Okay, then you can put 4 first, then you can put 2 first, or whatever you want to put. So it's out of order. Okay, but a sequence is another way. Okay, they must be follow a rule. It must be in a very specific order. Okay, but mathematically the definition of sequence is nothing but a function. Okay, so let's get started with the definition of sequence first. Definition. Okay, mathematically sequence is a function. Okay, sequence is a function f. It must be a function f whose domain excuse me, whose domain, okay, is the set of natural number okay. So this function is assign each natural number another number. That's what it means. Literally, that's what it means. Okay, so the value f1, f2, f3, okay, are called the term. Okay, let me switch to another card that we call the term. Okay, the term of the sequence. Okay, so this term over here, terms is plural. We can call each number of the sequence such as as A1, A2, A3, okay, dot 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 dot, AN, and there's more, okay. So what does it mean by this? It means that you see the number 1, 2, 3, and n over here. All of this is the subscript right here. All of this is a natural number, right? So f of 1, f of 1 is natural number. So 1, 2, 3, 4, 5 is a domain. Okay. So f of 1 is nothing but a1. Okay. So a1, a2, a3, a sub n is nothing but is the output of the function. So a1 over here is actually it is f1, and over here will be f2, and over here will be f3, okay, and over here will be f of n. Okay, so a1, a2, a3, an over here we call terms of the sequence. All right, and because you see that because sequence is a list of number, right? Okay, so that list of number, it could be limited or unlimited. If it is limited, we call that sequence is finite sequence. Okay, so there are two types of sequence. So the first sequence we call the finite sequence. So let me use a different color here. Finite sequence. And the second sequence is an infinite sequence. Okay, the finite sequence is a sequence when we have a limited number of terms. Okay, limited number of terms, and infinite sequence when we have unlimited number of terms. Okay, so this has limited number of terms. Okay, and over here has unlimited number of terms. Okay, I can give you a quick example, something like this. What if I have a sequence like this? What if I have 1, 2, 3, 4, 5 until 10? So I stop at 10. So I have a list of number like this. Okay, and this follow a certain rule, right? You see that it jump by 1. Okay, it jump by 1. So and it stop at 10. So it jump by 1, right? So it jump from here to here. Okay, from here to here. So this jumping by 1, right? Jumping by 1. Okay, and it stop at 10. So we call that limit. We call it finite sequence. Okay, and I can have example like this for the infinite sequence. I can have something like 2, 4, 6, right? 8, dot 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 dot, and you see that there's no last term over here. So it's still a sequence over here, right? And it jump by 2, right? So this is jumping by 2. By 2, and there's no last term. So that's why we call that infinite sequence. For finite sequence, we have last term. Okay, and later on in the next section, I'm gonna just talk a little bit about that. And the next section we're going to talk about two kind of sequence. Also, the first type of sequence is we call that geometric sequence, and the second one we call that hopefully I'm sure that you guys already heard that the second one we call it a arithmetic sequence. Okay, but I don't want to talk about that in this video, because in this video we just kind of take a overview of what sequence and series what it look like. Okay. Right. And other than this, okay, we also have let me give you another. Okay, so this is a sequence. Okay, so I already give you. I think it's enough for you to understand what the sequence look like. Okay, and we have two methods of generating relation for a sequence, because you see over here, it doesn't matter if it's a finite sequence or infinite sequence, it follow a pattern, right? It follow a pattern. So there are two ways to generate a relation, the relation of for a sequence. Okay, and first way we use a recursive formula, and the second way we use explicit formula. Okay, so let's talk about that. Two methods of generating sequence pattern. Okay, I think I'm gonna put two method of generated. I don't know, so we should use this word. Two method of demonstrating. I think that should be better. So demonstrating sequence pattern. So the first one, we use recursive formula. Okay, and the second one is to use the explicit formula. Okay. So what is recursive and what is explicit? Let's talk about that. Recursive formula is a relation between the n term. Okay, so the relation between the n term, because this is over a1 is the first term, a2 is the second term, a3 is the third term, a sub n is the n term. Okay, it's the relation between the n term and term on all the term of some term preceding it. Okay, preceding it. Okay, that's the recursive formula. And a typical example of recursive formula is a formula to represent Fibonacci sequence. So example. Hopefully I have enough. Look like I don't have enough space for this, so I think I'm gonna erase this. Then let me talk about the example first. Then I'm gonna talk about that. Okay, example Fibonacci. You guys know what Fibonacci sequence look like. Fibonacci sequence is 1, 2, 3, 5, 8, 13, 13, 21. Okay, So Fibonacci sequence is infinite sequence. Okay, so this is I'm gonna spell his name. Fibonacci. Okay, sequence. Okay, and I want to generate the recursive formula to demonstrate the sequence pattern of this Fibonacci sequence. Okay, so what do you see? You see over here that this term, the third term is nothing but the sum of the first two terms, right? And the third term and the fourth term is the sum of the first two terms preceding that. So I can write recursive formula for Fibonacci sequence is a sub n is equal to what? Equal to a sub n minus 1, right? It's a term before that, and plus to another term before that. So equal to a sub n minus 1 plus a sub n minus 2. So this is, for example, a4, right? A4 is equal to a3 plus a2, right? This makes sense because a4 is 3, right? A4 is 3 is going to be a3. A3 is the third term, right? Equal to 2 plus a2 is the second term is 1, right? So a2 plus 1 equal 3, right? So that is how to get recursive formula. So you see that recursive formula is a relation between a sub n, okay, a sub n, and all the term or some terms preceding that, All right. Let me fix this a little. Okay. All right. And the second way of demonstrating sequence pattern, we use something called explicit formula. Okay. So pull this down a little bit. More space here. Explicit formula. Okay. What is explicit formula? Explicit formula is a relation between a sub n and it's not a relation. It's this a sub n is a formula of a sub n in term of n. Okay, it means that a sub n equal to something on the right hand side, and on that right hand side all you can see is the n. Okay, you don't see anything else. Okay, for example, I have a sequence like this: 1, 3, 5, 7, 9. And you see over here, each new term is jumped by 2, right? So I can get the explicit formula for this infinite sequence. It will be a sub n equal to 2n minus 1. Okay, 2n minus 1. You can look at that. The second term will be 2 times 2 is 4. 4 minus 1 is 3. Okay, and the third term will be a3, right? A3 will be 3 times 2 is 6. 6 minus 1 is 5. Okay. So this is very easy sequence. Okay, that's why you can get the explicit formula easily. Okay, some infinite sequence is very hard for you to generate explicit formula. Okay, and we're going to talk about this type of sequence in the next section. Okay, we can look like that this sequence is a arithmetic sequence right here. Okay, we're going to talk about that. So let me see. Let me check for sure that this is a arithmetic sequence or not. Okay. Yes, and this is a arithmetic sequence. We're gonna talk about that later. Okay, but in this video, I just want to show you that. Okay, from if you given us a certain sequence, an infinite sequence, you can generate the explicit formula. Okay. Or you can also generate a recursive formula. Okay, but sometimes it's harder to get the explicit formula. It depends on the given sequence you have. Some given sequence is very hard for you to find the explicit formula. Okay, but this one is very easy. I'm going to show you how to find the explicit formula for such type of sequence next section. Okay, next section. Alright, I can give you another example of explicit formula. What if I have something like this? What if I have 1 over 2, 2 over 3, 3 over 4, 4 over 5, and 5 over 6, and I stop right over here. So look like this is a finite sequence, and I can get the explicit formula for this finite sequence with a sub n equal to n over n plus 1. So you see that over here a sub n is written in terms of n only. Okay, it's not written as the sum or the difference of the preceding term of previous term, but this is to be written in terms of n only. Then all you can see over here is n and number. There's nothing else. There's no a sub n minus 1, and you don't see a sub n plus 1. You don't see any of that. Okay, just in terms of n. All right. Or you can have some explicit formula like this. You can see something like -1 raised to the n, a sub n equal to -1 raised to the n over 2 to the n power. So you see that a sub n over here is in term of n and n over here only. So this sequence is kind of it's a fraction. It's alternating. Okay, you see that all the term is the sign of each term is kind of alternating between positive and negative. It depends on n is even or odd. Okay. So in the next time, in the next few minutes, I'm going to show you how to find the term given explicit formula or given a recursive formula. All right. We can also differentiate a sequence. It depends sequence in the way that its sequence is conversion or diversion. So next, I want to talk about conversion and diversion sequence. Okay. Let me see. I think I'm gonna put the star over here. First one is a definition. Okay. I think I should use this as the second part. Okay, so this is the second part right here, and I should write it as let me use yellow one. Okay, two method of demonstrating sequence pattern. And the third part, and first that's when I'm talking about conversion and diversion sequence. Okay, we need to understand what conversion sequence is and what diversion sequence is. Okay, well, conversion, where you heard the word conversion, it looked like this come from the word converse, right? It means what? It means that you have when you have a sequence, and it's an infinite sequence. Okay, it's not finite, and that sequence is gonna get closer and closer to a certain number. Okay, then we call that sequence conversion sequence. Okay, so conversion sequence is infinite sequence. Okay. Okay. Is getting closer and closer to some value. Alright. For example, I have a sequence like this, and I say that this sequence is getting closer and closer to value 0. Okay, so I have the explicit formula for this sequence. A sub n equal to 1 over n. Okay, and if you go ahead find all the term, okay, all the term of this sequence. For example, I'm going to find the first 5 term. Okay, so a1 will be equal to 1, right? a2 will be 1 over 2. a3 will be 1 over 3, right? And a4 will be 1 over 4. a5 will be 1 over 5. So a100 will be 1 over 100, right? So the bigger the n value, the smaller the output, right? So if n is a trillion, and you will have 1 over trillion, and 1 over trillion will give you what? It give you 0. Okay, it give you 0. So the bigger the n value, the smaller a sub n. Okay, so the bigger the n, the sequence will be reached closer and closer to 0. Okay, so in this case, this sequence a sub n is conversion sequence, and it conversion to 0. Alright, it's conversion to 0. So that is conversion sequence. Then what is diversion sequence? Okay, diversion sequence, it should be the other way around, right? It means the sequence that never converts. So diversion sequence, okay, it's an infinite sequence again. It's going to be infinite sequence which never converts to any value. Alright, how about this? I can give you a typical example of what the diversion sequence looks like. For example, a sub n equal to n squared. Look at that. It's getting bigger and bigger. If n equals 5, then it will be 5 squared, it will be 25. If n equals to 100, then it will be 100 squared. If n will be 1000, it will be 1000 squared. You see, the bigger the n value, the bigger the a sub n. So it never converts to any value. Okay, this sequence here never converts to any value. And that's why we call that diversion sequence. Alright. So that's all you need to know about sequence. So next I'm going to give you few examples to help you to understand and to have you understand more about sequence, and to have you to do homework. Okay, so let's start with our first example. Okay, example. I'm gonna think. I think I'm gonna put practicing exam. Alright. So first one, I give you explicit formula given a sub n equal to n squared minus 1. Okay, and I want you to find the first phi term of this sequence. Answer. Very easy. This example is very easy. So find the first phi term, right? It means you want to find A1, A2, A3, A4, A5. So A1 will be n equal 1, so it will be 1 square minus 1, so it will be 0. A2 will be 2 square minus 1 will be 3, so A3 will be 3 square minus 1 will be 8. 4 square minus 1 is 15. 25 is going to be 5 square, right? 5 square minus 1 gives you 24. So the first phi term of this sequence will be 0, 3, 8, 15, and 24. So that is how you find the terms of the sequence. You just plug it in 1, 2, 3, 4, 5, the first phi term. Okay? Alright. How about if they give you the recursive formula? So how are you going to do that? Example 2. Example 2. Given A1 equal 1 and A sub n equal to 3 an minus 1 plus 2. An minus 1 it means the term before preceding the A sub n term. Okay. Again, find the first phi term of this sequence. Well, it looks like they already give you the first term, right? So they already give you the first term. So the first term is A1 equal 1. And how about A2? A2 will be 3 times 2 minus 1, right? A2 minus 1 plus 2, right? So it will be equal to 3 A1 plus 2, and A1 is 1, so it will be 3, 1 plus 2 is 3, 3, 1 plus 2, 3 times 3 is 9, so that is A2 is 9. And A3 will be 3, A3 minus 1 plus 2. I just replace n with 3, so it will be 3, A2 plus 2, so A2 is what? A2 is 9. 9 plus 2 is 11. So give you 33. Okay, and you're gonna do similarly for A4 and A5. So I'm gonna have A4 equal to 105, and A5 give you 321. Alright, so that is how you find the term of the sequence given recursive formula. Okay, very good. All right. Now, how about this? Example 3. Now, I don't give you recursive formula or explicit formula anymore. I'm gonna give you the infinite sequence. Okay, for example, in this case, I give you the sequence like this: 1/2, 3/4, okay, 3/4, 5/6, 7/8, dot 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 dot. So this is an infinite sequence. Okay, and the question that I ask you to find, okay, explicit formula for the above sequence. Alright, so how we do that? So in order to deal with such type of question, you must be able to recognize the relation between the first term and the second term, the third term and the fourth term. So what do you see over here? What you see over here is that look like this is jump by 2, right? Look like this is at the bottom here, on the numerator, on the denominator jump by 2, and on the numerator also jump by 2. Okay. And what else you see? So write the explicit formula. Sometimes it's very hard. Okay, so a sub n will be equal to 1. So you just need to find. So this is also jump by 2, and it's jump by 2. Okay, because you never learn how to use. You never learn arithmetic sequence. Okay, so it's kind of a little bit hard to write explicit formula. So because it's jump by 2, so I can write the numerator will be 2n minus 1, right? And the bottom is jump by 2, so will be the first term is to the second one will be 2n, right? See, if n equal 1, 1 times 2 is 2, n equal 2, it will be 4. So the bottom is easy to find. Okay, the first one is kind of a little bit harder. However, as long as you know how to you understand arithmetic sequence when I do the second video, this cover the second section of this chapter, then you should be okay with that. But now, because you have not learned arithmetic sequence, so all you have to do is you have to open your eyeball and see the relation between 1, 3, 5, 7 and try to get it in terms of it. Okay, so that is kind of a little bit hard. Okay, all right. Or I can give you a sequence like this: -2, 4, -8, 16, -32, and you see that first term, second term, third term, fourth term, and fifth term is kind of, all the signs kind of alternated between negative, positive. So negative, positive, negative, positive. So in order to get the explicit formula for this, okay, because the first term is negative, so you're gonna have a -1 raised to the n. See, if n is 1, right, so it will be negative, n is 2, give you positive. And because this is 2 times 2 is 2 times 2 is 4, 4 times 2 is going to be the first term will be 2, will be 2n. Alright, so first n equal 1 times 2, right? And equal 2 is positive, 2 to 2, 4, 3 with 2 times 3, 2n does not look like it's good, right? Because with the 2n and 3 times 2 is 6, it doesn't work for that. So this one is not good. How about 2 and 4 is 2 squared, 2 to the third, 2 to the 4. Oh, how about it? 2 to the n power. That's better. Here you go. This one is much better because it looks like 16 is 2 to the 4, 32 is 2 to the 5th power, 82 to the 3rd power. Okay, so that is how you find explicit formula for the sequence for infinite sequence. You have to find the relation and try to get write a formula in terms of n. Okay, all right. Okay, so after you understand what sequence is, on the second part of our video, I want to talk about the second concept. It is series. What is series? Okay. So we know that the sequence is nothing but is a set, but that set must follow a certain rule, right? Series is nothing but is the summation of all the term. Okay, it's the summation of all the term. Okay, so I'm gonna put over here the first. I'm gonna talk about definition. The sequence of series. So definition. So a series is a summation of terms of let me see how I'm gonna express that because you can add the first 3 terms or you can add all the terms. So I'm just saying it's a summation of terms. Okay, term of a sequence. Okay, term of a sequence. And because it is summation, so we're gonna use some Greek notation, Greek symbol to represent for this summation, and the Greek letter over here I use to represent this series or summation is sigma. Okay, so the series, we use sigma notation to represent series or represent the summation. So series notation will be sigma. So this means sigma. Okay, so this is means sigma. Okay. Alright. Okay. But when over here, when I say summation, like how many terms we want to do the summation for? That's the question you want to ask, right? What if I want to add only summation to mean addition? What if I want to add only 2 terms, the first 2 terms? What if I want to add only the third 3 term or the third 5 term? Okay. Then do we still call it summation? The answer is yes. We still call it summation, and we still can use sigma notation to represent that summation. But there's another way to represent that notation, where we use something called partial sum. Okay, partial sum to represent summation of a certain number of terms in the sequence. Okay, for example, if you want to you want to do the summation for only 2 terms, say I can write it as S sub n. This mean sum. Oh, I'm sorry. It will be S sub 2. I'm sorry. So S sub 2, it means the sum of the first 2 terms. Okay, so if S of 3 could be a sum of the first 3 terms. How about S sub n? S sub n. S sub n will be a sum of n terms. Sum of n terms. Okay, so it depends on how many terms you want to add them up together. Okay, then we can write. It depends on the number of terms you want to add up. Then you can use S sub of some number correspondingly. Okay. All right. Okay. If we have n partial sum, so the partial sum it means the sum of n of all the term of the first n term, we call n partial sum, and we can write S of n, right? And S of n is nothing but sigma. Okay, if we want to use the sigma notation, okay, it's sigma from k equal 1 to n of ak. Okay, I know you understand this. So let me explain this. So S of n is the summation of the first n term. Okay, can be written as the sigma notation from 1 to n of the sequence a sub k. Just think about it. A sub k, you replace that. So a sub k, if k equal 1, you're going to have a1, right? If k equal 2, will be a2 will be addition, right? Because we're talking about sigma notation, so this will be addition plus a3, right? If k equal 3, if k equal to n, then we're gonna add up to a sub n. So that will be equal to S sub n. Alright, so I'm gonna box this. There you go. Alright. Alright. So in order to make it clearer, let's go through the example. What if I have a sequence like this? A1, A2, A3, A4. Okay. And I want to add the first 3 term only, so it could be S3, right? I'm gonna add the first 3 term only. Okay, it means S will be A1 plus A2 plus A3, right? Okay, so this is partial sum notation, and this partial sum notation can be written as the sigma notation. Okay, it will be AK when K is from 1 to 3. Okay, so this is a partial sum of the first 3 terms. Okay, you can write partial sum of all the terms. Okay, so S sub n is n term, we don't know because it's an infinite number of terms. So S sub n is nothing but the sigma notation from k equal 1, right, to n, right, of ak, right? Okay, and if n is infinity, right? If n is infinity, then we're gonna have we can write sigma notation of k equal 1 infinity of a sub k. So if n equal infinity, then we can write like this, right? Okay. Alright. Before I'm doing some more practicing problem, I want to talk about some property of summation. Okay. And there's some summation rule. There are few summation rule you should memorize. Okay. So on the second part of the series, I want to talk about property. Okay. Of sum. Okay. The first property I want you to memorize is, if you have sigma notation summation, okay, of two sequence AK and BK, then sigma of two sequence will be equal to the sum of each sigma. Okay. This might be a little bit different. So okay, so that's the first formula I want you to memorize. The second formula is that if you have sigma of the difference between two sequence, then it gives you the difference of two sigma. Alright, and the third one is that if you have sigma of the scalar of the sequence, okay, C over here is a number, scalar, okay, a number, a constant. So this will equal to C times, so you can remove the C into the front, K equal 1 n of AK. Okay, so this three formula is very important. Okay, so next there are only three actually. There are three summation rules I want you to memorize. And probably this rule is very helpful. It's probably help you when you go to calculus level. So that's why I want you to memorize this. Summation rules. Maybe in homework you have to use it. Maybe. Okay, I don't know, but it look like that because right now I see this in the textbook. So it look like that you probably have to use it. Okay. The first rule is, if we have sigma notation from I from 1 to n of I, then it will be equal to 1 plus 2 plus n, it will equal to n plus 1 over 2. Okay, so you add all the number and you can use this formula to find the sum. That's what it means. Okay, B, you have I from 1 to n of I square, you have 1 square plus 2 square plus n square, right? Then you will have n equal to n plus 1 times 2n plus 1 over 6. Okay. And the third one is if you have n from 1 to n of n3, so you have 1 square plus 1 cube plus 2 cube plus n cube equal to n square plus n plus 1 square over 4. Okay, so this rule over here is very helpful later on. Okay, so make sure you memorize it. Okay, or at least you memorize the first two. Okay, all right. Now let's jump into some practicing example. Let's see. Okay. For example 1. Okay, let's see. Let's see. Okay. Find the sum of this series k equal 1 to 5, k from 1 to 5 of k squared, and we want to find the sum. Okay, very easy. So you get 1 will be 1 squared, right? Plus k equal, because it's from 1 to 5, so k equal 2 squared, k equal 3 squared, 4 squared, 5 squared. Go ahead, add them up. It gives you 55. Very easy, right? So all you need to do is you do the substitution. All right. Example 2. Right. Okay, let me write. Use sigma notation. Okay. To derive the sum for the following summation. So I have the sum of how many terms? 1, 2, 3, 4, 5, 6, 7. So there are two parts. So the first one is 1 cube plus 2 cube plus 3 cube plus 4 cube plus 5 cube plus 6 cube plus 7 cube. Okay, you see that there's 7 terms and all of them is raised to the third power. So I can use sigma notation to be I from 1 to 7, right? Because there's 7 terms, and will be I to the third power, right? Or you can use over here k from 1, then you can change it to k to the third power. It doesn't matter. Okay, you can use any letter you want. Okay, part B. We never have something like this: square root of 3 plus square root of 4 plus square root of 5 plus dot 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 plus square root of 70. Okay. So how many terms we have? From 3 to 70, we have from 1 to 70. From 1 to 10, we have 10 terms. Right? From 1 to 70, we have 3 terms. We have 70 terms, but over here from 3 to 70, so we will have only 68 terms. All right. So you can put I. So 68 terms, and you can write. 58. Oh, you can write like this. Or you can write, because over here 3, 4, 5, 6, 7. So you can write from I from 3, okay, to 70 of square root of I. Here you go. That one is easier. Okay, that makes more sense. Okay. Because if you want to start from 1 to 68, you can, but it's kind of a little bit harder because you probably have to use the arithmetic sequence. Yeah, because the square root of 3, square root of 4, square root of 5, so it jumped by 1. So you probably have to use arithmetic sequence, but you never learn arithmetic sequence until next section. So I think this way you should start from 3 to 70 instead of from 1 to 68. You know, and we're going to put square root of I, and because I is from 3 to 70, so it will be 3, 4, 5, 6, 7, 8 to 70, and the summation is when you add all the terms together. Okay. All right. So it's very easy, right? It's nothing hard because it's actually this concept is very hard, but it's not at this level. It's not in pre-calculus, so don't worry. It's going to be very easy. Okay. All right. Let's see what else. Probably I probably missed another formula. Let me go back here. Look like I missed another formula. It will look like this is what ABC. So let me add another formula. So the fourth one will be sigma. Okay. K from 1 to n again of a constant number. Okay, then this is equal to n times c. There you go. Alright. Alright. Let's see anything else. Let's see. Okay. How about this one? Example 3. Let's do one more example before we start. Example 3. Oops. Example. Oops. Still here. Still. So let me shift to. Okay. Okay. Use summation property and rules to find the sum. Okay, to find the sum. So the question given like this. I have sigma notation from 1 to 14 of 2i squared minus 3. Okay, so this is a sigma of the difference. So if you use the property, you can split them up. It will be difference of the sigma. Okay, so it will be difference of each sigma minus from 1 to 14 of 3. Okay, for this one, you see this is a constant right here. You can use the third formula, the third property. So I can write 2 in the front, right? You can move 2 in the front. I squared equal to minus. You can use the 4 property. So this is n over here is 14. So you can write 3 times 14, right? This is the 4 property. And now over here is I squared. I squared, you can use the second rules. So this can be written as 2 times 2 times what? The formula will be n plus 1. So n over here is 14. So let me write the formula. So n plus 1, 2n plus 1 over 6, right? Minus 3 times 14. 3 times 14 is 42, right? Okay, and n is 14. Okay, n is 14 in this case. So I'm going to plug it in. 2 times 14 plus 1, 2 times 14 plus 1 over 6 minus 42, right? And you calculate amount, so you will have 2 times 14 times 15. 2 times 14 is 28, it will be 29 over 6 minus 42, and you put everything into calculator. You have the sum of this sigma notation is 1988. Here we go. So that is how you use the property and the rules to calculate this sigma notation to find the sum. Alright. So I think that's all for this section, 12.1. It's not really that hard yet, but again, you have to do a lot of practice. Keep up with your homework, then everything will be fine. Alright, and make sure you master this concept so that you can prepare for the second section of the chapter. Okay, I'll see you next time. Bye bye.